We are on our way to building our own homemade op amp as a way of understanding in principle, not in great detail, but in principle, how an op amp is built up from individual bipolar junction transistors. Remember we first saw how amazingly useful op amps were, and now recently we've studied several common transistor-based circuit fragments so that we can see how individual transistor-based amplifier elements are built up. And then, not this lab, but the next one after that, we're going to make highly simplified homemade op amp. So you see in principle how an op amp does its magic. So the biggest missing piece from building up our own homemade op amp is the differential amplifier. So this is the input stage of our homemade op amp. So this is the topic of lab 16. Actually, I've drawn this twice. So actually what I drew over here on the right side is the circuit as I built it. Well, there's a couple of embellishments we'll add in a moment. But I adjusted some of the component values because we're working with plus or minus 9 volts, whereas the lab was originally designed for plus or minus 15 volts. And so it's a combination of just making things scale nicer to 9 volts and also trying to use parts that we have in our kit. I changed these collector resistors from 15K to 10K. Actually, there's only one, right? We'll remove one of these in a moment, but I want to draw them both for symmetry, but one of them is optional. So this went from 15 kiloohms to 10 kiloohms. And this emitter resistor, there's one on each side, went from 150 ohms to 100 ohms. And this tail resistor went from 15 kiloohms to 10 kiloohms. Okay, and we'll eventually replace this with a current source, but for the moment it's a tail resistor. Okay, but first let's try to work through where the gain expressions for this circuit come from. And so you might remember from the reading, I wrote down the results so that we know if we get to the right place in the end. The common mode gain is minus the collector resistor divided by 2 times the tail resistor plus the emitter resistor plus the little Re, which is the dynamic resistance of the base emitter junction, as seen from the emitter side. And the differential gain is Rc over twice, okay, and then in the parentheses we have the emitter resistor plus little Re. And then remember, the differential gain is the output voltage divided by the differential input, and the common mode gain is the output voltage divided by the common mode input. And the definition of the common mode input is the average of the inverting and non-inverting inputs. And the definition of the differential input is the difference of the two inputs. You have to watch out for this factor of 2 here in these two expressions. So let's see if we can work out let's start out by seeing if we can work out the common mode gain. So when you look at this circuit, especially when I include both collector resistors, even though in the end we usually remove the one where there's no output, you can see a certain amount of symmetry, and we're going to exploit that symmetry. And we want to put in a common mode signal, so I guess we will put in a signal delta V over here. We'll put in that same signal delta V over here, and I guess what that's saying is that VCM equals delta V because it's the average of these two things. Okay. So we're going to wiggle both inputs at the same time by delta V and see what happens. And we're taking the quiescent input condition to be that each one of these voltages is 0. So the key trick that we use to analyze this circuit for the symmetric case, actually it works for the anti-symmetric case also, is we will replace this tail resistor. So remember, if I have a resistor R, it is the same thing as if I take 2 resistors in parallel, each one of which has value 2R, because you know that 2R parallel 2R is R. So let's replace the tail resistor with 2 copies of itself, but with each copy having twice the resistance. So we will put one tail resistor down here. I deliberately didn't practice this so that it sounds more spontaneous to you. And let's put the other tail resistor over here. So this is 2R tail, and this is 2R tail. But this is not quite right yet because there is a connection here. So there is still this connection. And then, meanwhile, this is still this is basically, well, in this circuit, this is plus 9 volts, this is minus 9 volts. We're calling this VCC, VEE, the 2 power supply voltages. Okay, this is exactly the same circuit. Now, we apply a delta V. Oh, and by the way, you notice if you cover up half of the circuit, then it basically looks like the familiar common emitter amplifier. Remember, our common emitter amplifier just looked like, here's VCC, and here's the collector resistor, and then here's our input, and then here's an emitter resistor, and then this could be VEE. Sometimes that was ground, sometimes it was a negative voltage. So it seems like, the sum of these resistances is playing the role of the emitter resistor for 1/2 of this kind of symmetric pair. Okay, so this goes up by delta V. This goes up by the same delta V. So everything is the same here. It's the same collector resistor, same emitter resistor, the same 2 times R tail. So if we just cut this thing down the middle, then there should be perfect symmetry. And it's the same voltage applied here, same voltage applied here. So if it's perfect symmetry, then there should be no current flowing either from left to right or from right to left over here. Because, by symmetry, which way would it go? There's no preference for it to go one way or the other. This voltage is the same as this voltage, so there's no current flowing across this red wire. So therefore, for the purposes of analyzing a symmetric signal, we can erase the little red wire. So that would give us, so just taking it totally at face value as it is now, let me just find the right place to write something down. That would give us a common mode gain. Well, right, so this is V out in terms of delta V. I guess we could say that. So we'll say V out over delta V. But by the way, that's the same thing, I think, as saying V out over VCM, which is the same thing as saying the common mode gain. So that is, so we'll just use this expression, right? Remember, for the common emitter amplifier, oh, and this was our output. We had delta V out with respect to delta V in for the common emitter amplifier was, well, first we just wrote minus RC over RE, but then we said, well, we could be a little smarter about that because there's actually this little RE, which is the dynamic resistance of the base emitter junction. Remember that little RE is basically dVBE DIC, and it is 25, at room temperature, it's 25 millivolts over IC. And it sort of behaves as if it were a little resistance in series with the emitter. So this is like little RE, and this is like little RE. So it's like a little dynamic resistance for AC signals inside the emitter. At least in terms of how you analyze things. Okay, so where were we? So we said, instead of minus RC over RE, we actually had minus RC over RE plus little RE. We'll put that in parentheses, I suppose. So we'll do the same thing here. So this should be minus, and then we have the collector resistor up top. And now, what plays the role of the emitter resistor? Well, there is the emitter resistor, but there's also this 2R tail, which combines with the emitter resistor, and then we have little RE. So we have 2R tail plus the emitter resistor plus the dynamic resistance of the base emitter junction of little RE. And lo and behold, that is the expression that we intended to derive. We didn't even practice this in advance. That's amazing. I did write down the correct answer, though, so that if we didn't land at the right place, we could go back and fix our mistake. So that's good. We did that. So we did the common mode case. And it's basically just like analyzing the common emitter amplifier, except that the key trick you have to use is you're applying a symmetric voltage difference to both sides. And because of that symmetry, well, before you apply that symmetry, you can split up the tail resistor into 2 copies in parallel, each of which is twice our tail. And then we have this connection. So this is the same circuit as this. We just took the tail resistor and made 2 resistors in parallel, each one twice as big. But because of the symmetry, we know there's no current flowing through this red line. And therefore, we can analyze each half separately, and as if it were just a common emitter amplifier. Okay, so that was fun. So now we want to use a similar trick to get the differential case. So let's think how that is going to work. So in this case, well, we have to be a little careful about the difference in a factor of 2. So let's apply plus delta V over here, and we'll apply minus delta V over here. And in that case, so this is V in plus minus V in minus. So I guess in this case we have V diff equals 2 delta V. So that factor of 2 is important because we have V in plus is plus delta V, V in minus is minus delta V. So the differential voltage we're applying is 2 times this thing we're calling delta V. Okay, let's also make a little space to do some work. And so this is a totally anti-symmetric case. So if this goes up by 1 volt, this goes down by 1 volt. So in that case, I think in this case, it's easier for us to combine the tail resistor back into its one resistor. So the argument we're going to make, let me just step back to the argument we're going to make is when we increase this delta V, we're going to increase this current. And then we're going to decrease this delta V, so we're going to decrease this current. So we could call this like a delta I, and then actually the corresponding delta I over here is in the opposite direction. because we have, we've lifted this up by delta V. We've pushed this down by delta V. So there's a little more current flowing over here, but there's a little less current flowing over here, and those two currents offset one another. So in fact, there is no change in the tail resistor current. Yeah, I think to do this, see again, I didn't practice it because I think you benefit from seeing me have to think through it and talk out loud about it, as long as I don't make any significant mistakes. So we'll put the tail resistor back the way it was originally. So increasing this base increases this emitter, which then increases the current flowing this way. Decreasing this base decreases the voltage of this emitter, which then decreases the current flowing this way. So you could say it's a delta I flowing that way. So this delta I is the same as this, delta I. Do we want to be more careful about that? So there's some quiescent voltage here at this point, which is this voltage, I suppose. I'll call that X. So the quiescent Vx is just V E E. Usually you make these uppercase E's, not lowercase E's. VEE plus 2 times the quiescent collector current. I mean, it's, collector current on one plus collector current on the other times R tail. And I guess if you want to separate the two collector currents, we could call this IC1, and we can call this IC2. Okay, so if we call this IC1, we call this IC2, then we have, so I guess we could say, if we want a little more careful, we can say, right, Vx is VEE plus IC1 plus IC2 R tail. And I guess that's true whether or not it's quiescent. And so then we're going to say that, okay, then we're going to say IC1 is approximately the same as IE1, right? Because we're in the active mode, the base current is very small. So let's say IC1 is approximately the same as IE1, and that seems like it should be Vn. I guess we can say Vn plus minus a diode drop. Okay, so there's V in plus minus a diode drop. So there's the emitter voltage over there. And then we're going to divide by whatever Vx happens to be. And then, or subtract whatever Vx happens to be. And we can divide by this emitter resistance. And then there's something similar for IC2. So this is IC2, which is basically the same as IE2. And that would be V in minus a diode drop. And then minus whatever this X voltage is. And then divide by this RE. And if we say that V in plus, so we're going to say, I guess we start out at 0, and we just apply a wiggle here. So this is plus delta V. And then this V in minus is just minus delta V. So we have changed IC1 from its quiescent value by the same magnitude as we've changed IC2 from its quiescent value. So we have not changed, we call this I tail, which I guess is the same thing as IC1 plus IC2. So we've increased IC1 and we've decreased IC2 by the same amount, right? I guess if you want to call this a delta, so you could say, okay, so I guess I'm arguing that Vx didn't change here because IC1 plus IC2 didn't change here. Maybe that you could call that a circular argument. We could try to avoid that. I guess we could try to avoid that. Maybe we don't have to. I think it's a pretty decent argument. So we increased this voltage, which increased this current. We decreased this voltage, which, decreased this current. So we're saying the delta I is in that direction. So whatever increase in current comes from here is exactly offset by the deficit in current here. So this excess of current flows totally across here. That excess in current does not have to flow down into the tail. So Vx does not change as a result. Yeah, when you increase delta V and decrease delta V by the same amount, this is plus delta V, this is minus delta V. This delta I is the same size as this delta I, so therefore this Vx does not change. Because this tail current doesn't have to change, because the sum of the two collector currents is going to be the same for an antisymmetric delta V. Okay, so then in that case, we have not changed the tail current. Okay, so then let's say what happens to the collector current, and then therefore what happens to the output voltage. So I think we successfully argued that when we apply this delta V, because we're applying a plus delta V here in the same size minus delta V here, Vx does not change. So in that case, let's work out what the change is in IC2. The change in IC2 is the same as the change in IE2, pretty close, which is minus delta V. So the diode drop doesn't change, And Vx we said doesn't change. So it's minus delta V over Re. Now, of course, when we say Re, really we want to include also the little re. Yeah, so that's good. And then, now we can say, here, let's make some room over here. Okay, so now we can say that delta V out is, oh, so remember, here, let me just write this. Before I say delta, remember V out is VCC minus IC2 RC, okay? So then the change in V out, so VCC doesn't change, so that's minus the change in IC2 times RC. And here's the change in IC2. So we have delta V out is minus, and then we have minus delta V over RE plus little re times RC. So that leaves us with delta V out is delta V times RC over RE plus little re. And we said that V diff is 2 delta V, therefore delta V is 1/2 V diff. So this is 1/2 V diff RC over RE plus little re. Yeah. So then we can write, as we intended to write all along, I guess, delta V out over V diff, which is called the differential gain, is RC over 2 RE plus little re, which is what we intended to get to over here. Wow, okay, that was kind of fun. So for the second part, the key was to notice that the voltage at point X does not change if we increase this voltage and decrease this voltage by the same amount, because this increase in current exactly offsets this decrease in current. So the extra current over here just keeps flowing over here, and there's no change in the tail current, therefore there's no change in voltage X. And then that therefore leaves the tail resistor out of the gain expression for the purely differential case. So then and then the factor of 2 comes from the fact that we applied plus delta V there, minus delta V there, so that's a differential gain, a differential voltage of 2 delta V. Okay, cool. So we did that. Good. So we wanted to do that derivation. Whoa. Now let's plug in results for the case that we're going to build over here. And again, in Circuit Lab, oh, well, one more thing. So if you want to, you can take an opposite out over here. You could say this is out and this is the opposite of out. In that case, you need both collector resistors. But if you're not, the convention is normally you're not using this output, you're only using one output. And therefore, if you want to, you can omit this collector resistor. It kind of makes you feel as if you've broken the symmetry. It only breaks the symmetry a little bit. It breaks the symmetry in the limiting case in which the transistor properties depend on VCE, the collector emitter voltage. That's the so-called early effect. You could leave it there, I guess, for symmetry. But anyway, the convention is that you leave it out because you don't need it because there's no output there. So in fact, we will do the same thing over here. We will leave it out over here also. It does no harm to leave it in, but the convention seems to be if you're not using that output, then you leave that resistor out. Okay, so now let's work out some numbers for this case. Okay, so here is the circuit under study. Now this circuit actually is usually used with DC coupling. So you do just put your inputs straight in here. There are no capacitors normally. And actually one nice feature of this circuit is it doesn't need AC coupling, and you can amplify you know, a DC coupled voltage. So as a matter of fact, if you just want something that behaves like a common emitter amplifier but doesn't have the capacitive coupling, you can build this circuit and you can ground one input and use the other input. So if you want an inverting amplifier, you ground this one and you put your input in here. Or if you want a non-inverting amplifier, you ground this input and you put your input in here, and you get some modest gain, you know, tens or something. It's not a gigantic gain. But this is actually one common way to use, I guess, 2 transistors and some resistors to get an amplifier that doesn't have the AC coupling hassle of a common emitter amplifier. But that's not what we're doing here in this lab. Now, we build this up using a little array, kind of a multi-transistor array. And it's kind of an expensive part. It's like a $20 part, and we don't want to zap it. So we're basically going to AC couple the inputs mainly as a way to protect the circuit from damage. So we have over here a resistor to ground. So this is ground, and I think we made this 10K ohms. And then over here we have another resistor to ground, which is 10K ohms. And then we just have a capacitor, which is, I think it's just a 1 microfarad capacitor. So here we have 1 microfarad. And so then this is our inverting input. And then over here, we have a 1 microfarad capacitor, and this is our non-inverting input. And the reason for that, again, is just to make it a little less likely that we zap the, this kind of expensive chip with unexpectedly big signals. So you don't, again, it's not mandatory, but we do it kind of to protect the chip. Okay. Then, so later we'll replace this tail resistor with a current source, but for the moment we have this tail resistor. So then let's work out what the quiescent collector current is. So, okay, so now putting this connection to ground makes it obvious that the quiescent input voltage on each side is 0. We assume that to be the case over there anyway, but now that kind of makes it more explicit. So when there's nothing happening, each base, remember, we have base, collector, emitter, base, collector, emitter. So when there's nothing happening, each base is at 0 volts. So here, the quiescent state. So we have the base is 0 volts. So then each emitter is a diode drop below 0. So you say minus 0.7 of a volt. So then we'll say what is each collector current. So I guess again we can imagine in your head the redrawn case where you have the 2 circuits in parallel, because the 2 collector currents together are going to go down through this tail resistor So then we have the collector current is this emitter voltage minus VEE. By the way, yeah, it is conventional to make these uppercase E's. And then the resistance is RE plus 2R tail, because if you were going to redraw it as that symmetric case, you would have 2R tail and then 2R tail. Yeah, and then, so then you have the two collector currents together going through one R tail. Okay, so what is that? So that is minus 0.7 of a volt, and then minus 9 volts divided by 100 ohms plus 10 kilo ohms. And we get, okay, we get about 0.82 milliamps. That's the quiescent current through each collector. So then that lets us work out what little RE is. So little RE is, at room temperature, it would be 25 millivolts divided by IC, which is 25 divided by 0.82 is 30.5 ohms. So then it seems like we expect the common mode gain to be minus 10 kilo ohms divided by 2 times 10 kilo ohms plus 100 ohms plus 30.5 ohms. Okay, and then we expect the differential gain to be 10 kilo ohms divided by 2 times, well, 130, well, okay, 100 ohms plus 30.5 ohms. Okay, and so then if we put in numbers for the differential gain, we get 10 E3 divided by 2 times 130.5, whoops, 10 E3 divided by 2 divided by 130.5. That is 38.3. $10,000 divided by 10 E3 divided by 2 divided by 130.5. Okay, 38.3. And the common mode gain should be, okay, so that is 10 times 10 to the 3 divided by, and then this is 20 E3 plus 130.5. So that seems to be about 0.5. It's like 0.497, so we'll say this is basically minus 0.5. Okay. And I think that minus 0.5 number is the same that you get using the conventional numbers for Circuit Lab. And I don't remember, I think you get a pretty similar gain also for the Circuit Lab circuit. Okay, so now we are actually set up. Oh, I'm going to write some pin numbers here, and then we're going to measure the differential gain first, because I'm already set up to measure the differential gain. Okay, so I built this circuit over here, and let me first, before I give you a whole tour, this resistor is the tail resistor. It's a 10K resistor, and I am, with these two probes, measuring the voltage difference across it. And the voltage difference, the voltage across this 10K resistor is 8.32 volts. Okay, cool. I just had a wait, what moment? So that didn't make sense because it was a factor of 2 different from what I expected. But that's because what we wrote here was 2R tail. Oops. So we want 2R tail. So this is 20 kilo ohms. All right. So we'll deal with that in a minute. Yeah, okay, so we think the quiescent IC, this is 8.3 volts, so it should be 8.3 volts divided by 20100. So that is 0.42 milliamps. And then 25 millivolts divided by 25 divided by 0.42 is 59.5 ohms. Okay, so this should be 59.5 ohms. I guess we could call it 60, but okay. And then this should be 59.5 ohms. Okay. So then I think it won't change the common mode gain. So you'd have 10E3 divided by 220E3 plus 159.5. It's still a half. But for the differential gain, we have 10E3 divided by 2 divided by 159.5. And we get, right, 31.3. Okay. Sorry. Okay. Good. So that was a worthwhile check. Look at that. I measured the voltage drop across the tail resistor. I said, well, it's a 10K resistor. And so it should be 2 times the collector current times our tail, which should be 8.4 volts. Okay, I see 8.3 volts. So it's a good thing we measured that because we made a little boo-boo in this calculation. All right, that was fun. Okay, now let's look through this circuit. So this was one case where I had a hard time trying to make the real circuit look like the schematic diagram. For one thing, when I put this 3086 array up here, so that pin 1 is the bottom left and pin 14 is the top left, then you'll notice that we drew the non-inverting input on the left is pin 9, and the inverting input on the right is pin 12, and so pin 12 is to the left of pin 9 physically. So actually, it might have been smart for us in this case to have taken the, well, I guess it might have been smart for us to have drawn this whole circuit mirrored. But, well, we didn't. So just bear that in mind. So in fact, the inverting input is on the left and the non-inverting input is on the right. Okay, so pin 11 up here should go to plus 9 volts. So pin 11 does go to plus 9 volts. That's right there. Pin 14 should go to plus 9 volts through a 10K resistor. That's up here. So pin 14 does indeed go to plus 9 volts through a 10K resistor. And then I'm also monitoring that with a scope channel And in case I forget later, that scope channel is AC coupled right now. It's channel 2 of the scope, and it's AC coupled. So I can subtract. I want to see the output signal without the DC offset in a moment. Okay. Then, let's see. So pin 9 is this base. So it should have a 10K resistor to ground and then a capacitor to the non-inverting input. So pin 9 is over. Here is pin 9. And there's pin 9. Okay. Pin 9 comes over with this little blue jumper wire to here. So here's the capacitor to the non-inverting input, which currently I've left disconnected. I can do that because it's AC coupled. And then I have this 10K resistor to ground. Then pin 12 is my inverting input. So pin 12 is this little blue jumper wire over to this blue capacitor. So on the near side of the capacitor, I have this 10K resistor to ground. That just sets the DC condition. And then I have connected to the far side of the capacitor. Here's channel 1 of my waveform generator. I'm only using one channel. Here's my waveform generator input. And here is scope channel 1. And I'm currently set up to look at the differential gain. To do that, I put a signal into the non-inverting input, and I did not. Actually, I put a signal into the inverting input. Sorry, I put a signal into the inverting input, and I put nothing into the non-inverting input, which is okay because the common mode gain is low enough that we're basically just measuring the differential gain that way. Then, what else? Then, okay, pin 10 should have 100 ohms down. Oh, here's R tail. R tail goes from -9 up to this point where I was probing with the voltmeter earlier. Then from there, we have 100 ohms going to pin 10, which is this emitter. So here's 100 ohms going to pin 10. And we also have 100 ohms going to pin 13. That's this one. And I think that's everybody. Okay, so now I'm going to try to measure the differential gain. So well, first of all, my power supplies are set to provide +9 and -9. And again, remember, the EE board has this thing called VCC, which is typically like a digital power supply. It's either +5 or +3.3, and we typically don't use it. So when I say VCC is +9 and VEE is -9, I'm meaning what the EE board calls VP plus and VP minus. Then WaveGen is a 25 millivolt sine wave. This middle C frequency is left over from a previous exercise, so I'll make this 1,000 hertz. Okay, so here's the 25 millivolt amplitude sine wave. We'll go over to Mr. Scope channel here, and okay, and I guess I can just press stop. So there's a little bit of fuzz on the signals, but if I go to channel 1, you should see 50 millivolts peak to peak. Let's see. Yeah, so you see this one goes from like 25 to -25. It's a little hard to see through the fuzz. And then channel 2 seems to be going from roughly -1 volt to +1 volt, but I was able to make a better measurement. So I used these cursors here, the red horizontal cursors, which are measuring the vertical numbers. So it seems like the difference between the bottom and the top here, the peak to peak voltage, I just kind of put it in the middle of each blob of fuzz, and I got 1.68 volts. So we have V out is 1.68 volts peak to peak amplitude, and V in is 50 millivolts peak to peak amplitude, because this was an amplitude of 25 millivolts, so it's 50 millivolts peak to peak, and this is 1.68 volts peak to peak. So if we divide 1.68 divided by 0.050, I get 33.6. So this is a measure differential gain of 33.6. That's pretty good. I mean, maybe there's a little uncertainty from the fuzz, and then I think there's also a little bit of amplitude dependence because we use such a small quiescent collector current. The little RE makes a difference, and the little RE, remember, kind of changes throughout the cycle a little bit. You get a slightly nonlinear response. So, right, because little RE changes as IC changes, as Vin changes. So, anyway, I think that's pretty good. Okay, so we expected a differential gain of 31, and we got 33 or 34. Okay, now let's go measure the common mode gain. The way I'm going to do that is here. Let me show you how I do that. So I have two copies of the same AWG signal. So before I had one going into the inverting input and nothing going into the non-inverting input. So now I'll just put exactly the same signal. Two copies of the same signal, one into each of the two inputs. So that should be a nice common mode gain measurement. And in the lab, you measure the common mode gain first, but I was all set up to measure the differential gain, so I did that first. So let's go back to waveforms here, and we'll run. And here, I can make this a little bigger. Let's make this 100 millivolts. I might even make it bigger than that. Let's see. So then, well, that's okay, I guess. And then let's put them on the same scale. So I'll make them both 50 millivolts per division. And you see it is inverting. And it seems like it could plausibly be a factor of 2. You can affect the fuzz a little bit sometimes. Okay, so then, in fact, I guess if I made this 25, oh yeah, I guess if I make this 25 millivolts per division, then they should appear to be about the same scale. Yeah. I wonder if I could say minus 25 millivolts per division. I've never tried that. No, I guess you can't do that. Okay. 25 millivolts per division. So that seems, whoops, hey. 25 millivolts per division. Yeah, so I'd say that's consistent with our expected factor of a half gain. Good. So I think we see what we expect for the amplifier in this form. The next trick is we are going to replace this tail resistor with a current source. And then remember, a good current source has, just like a strong voltage source has 0 source resistance. A good current source has infinite source resistance. So it'll turn out our current source has like a few mega ohms source resistance. So it's as if we replace this tail resistor with a few mega ohms effectively. Yeah, so in fact, I think I'm going to cut here and start a new video to convert the tail resistor into a current source.